All right, we're actually going to start. This is the official starting point of Calculus 2, Section 5 of Chapter 5. Yes, last class we had a review of the fundamental theorem of calculus, parts 1 and part 2, with respect to definite integrals. The fundamental theorem of calculus states that a definite integral of a continuous function can be calculated if there exists an antiderivative of the function. What does that mean? The definite integral, first off, what is a definite integral? What does it look like? That's what it is, but what does it look like? Yes. The integral, yes, it has bounds. The integral symbol, or the antiderivative. What this one's telling us is if f of x is a continuous function, if it has a antiderivative, meaning this is the derivative that came from some function. If we could find out what it is, then we can find the actual value. That's if there exists the antiderivative. That's what this is. It gets us back to the original function. Why is it called definite integral? Yeah, because it's bounded. It's the end result's going to be a what? Yeah, a number of some sort. An indefinite integral has no end. This one has an end because it starts someplace and ends someplace. Give me a value. But if we follow a line to infinity, what is the area under that curve? Yeah, we don't know. We can't get to it because it's indefinite. An indefinite integral of a function with respect to x an indefinite integral is the set of all antiderivatives of this function. It's not just one because it's an infinite number of them. The set of all antiderivatives of this function, and it's symbolized by this, has no bounds. And it does have an antiderivative, but we always have to put a c because there's two functions. The antiderivative of two functions are different by the constant that they portray, they convey. That's an indefinite integral. So all we do is find the antiderivative of the function and put a c behind it. No more done. So the connection between an antiderivative and the definite integral is this. So the connection between the antiderivative and the definite integral is this. So we have a bounded function. It's f is continuous, which equals the antiderivative of f is capital F of b minus f of a. That's how we defined it. But what this can represent also is we have two separate functions here. We have f of b plus some constant minus f of a plus some constant. Because remember, there are two functions here. So this is how we're connecting the two. Since it came from a bounded function, this now has to have the bounds. So what that means so the antiderivative of definite integral is this at the given bounds. The plus c now expands it, so we have f of b minus f of a. That came from f of x plus c, and this is equal to our indefinite integral on the given bound from a to b. There's the connection. The connection is our inclusion of that constant term. So the indefinite integral always includes what? What do you always have to make sure when you find an indefinite integral? What do you have to make sure? You always have that plus c. Right. Because again, we don't know what it is. And remember, c is a constant. If we take a derivative of it, what is the derivative of a constant? 0. So we get back to the original function. So that's our proof for it. So again, our definite integral gives us a number, but our indefinite integral gives us a function, a continuous function over anything it could be. Because it's the set of all antiderivatives in the infinite domain. All right, let's look at some examples and the next section. Oh, everybody finished writing this down? Because in this section, we're going to, again, the topic here, remember, is indefinite integrals and the substitution method. So let's talk about the substitution method. In integrals, this function here is actually the what? This function is actually the derivative of this function. So f prime of x is equal to little f of x. So what we're doing here, when we take an integral, we take the operation of the derivative and find out where the function came from. Last time we did something like this. So find me this answer. What is the integral of x cubed dx? Mm-hmm. X to the fourth over 4 plus c. How do you check it? Take the derivative of x to the fourth over 4 plus c with respect to x, and we're going to get x cubed. This value and this value should be the same. Then you did a proper antiderivative. You found an antiderivative. So let's put a formal definition of what we're looking at here. What we're going to be doing here we will be using the chain rule backwards. That's the substitution method. All right, so what we're saying here is whenever we deal with substitutions, we always say we're going to be using u. So if u is a differentiable function of x, and n is any number not equal to -1. So we have u as a function of x raised to a power. Then, using the chain rule, we get. Okay, do y'all remember what the chain rule was? Well, for example, if we had this equation, or our function was x squared plus 3x to the power 4, what's the derivative? Right, we have to first take the power, putting it out in front. So this becomes 4 minus 1, and leave the inside alone. And then you multiply by the derivative of the inside. Very good. That's the chain rule. So let's see how, this is what we've been doing. This is finding derivatives. Now, remember, we're using the function u. We're substituting the function u. So u of x is equal to that whole function, x squared plus 3x to the fourth. So it's u of x to the power 4. So the derivative is 4 u of x, 4 minus 1 du dx. Or more generally, u to the power n of x dx. The derivative of it is n u n minus 1 of x times du dx. So that's the chain rule. That's just a review of the chain rule. How does this relate now to integrals? With integrals, we have to be able to go from this back to this. So in order to be able to go back to this, we have to make sure we have all of these conditional parts. But the coefficient has to be the exponent of the original question. The exponent is to be 1 less than the original. You have to have the function times the derivative of that function. So here's the integral rule of the chain rule. So basically, we're using the chain rule backwards. Oh, I forgot about these guys. So for our original function, we have u n plus 1 over n plus 1. That equals u to the power 1 du dx. All right, so the antiderivative of our function u to the power 1 du dx. Remember, this is our u, so we take the derivative of the u, leave the u alone. Then we take the derivative of u. All this is being taken with respect to dx. So since this is our derivative, this is this part. Where does this come from? It comes from this. We started off with this. So our answer is u n plus 1 over n plus 1 plus c. There's a chain rule backwards. Okay, we're going to do a couple of examples to make it look much easier. Or we could just say the integral of u to the power n du is equal to the u n plus 1 over n plus 1 plus c. Because if you think about that, du dx is the derivative of u, and then we take the derivative of the whole function. So let's look at the first example. Oh, what is du equal? How does this relate back to this? What is du equal? Because here's u of n, u to the power n. That means anything else behind it has to be du. Du dx dx. Let's look at our first example. Find this indefinite integral. X cubed plus x to the power 5, 3x times 3x squared plus 1 dx. Use the substitution method and let's solve for the integral. How do we start off? What do we have to do first? Here are the steps. Define u. Then find du. So what's, in our case, what is u? Yeah, it's got to be the largest exponent because the derivative is always smaller. So this one is the x cubed plus 3, or x cubed plus x, I'm sorry. So what is du? Yeah, 3x squared plus 1. So fortunately for us, this makes our equation u to the power 5 du dx. This is du dx, which becomes u to the 5 du, which is exactly what we want it to be. Because if we're in this form, then our antiderivative is simply leave the u alone, just change the exponent. So the answer will be u n plus 1 over n plus 1 plus c, because it matches these two conditions. Here's u, that's u, and this is du. Since it matches our condition, All we have to do here is take our function, 5 plus 1 divided by 5 plus 1. And there's our answer. Always check your answers. So how would you check your answer? Yeah. Check your answer. So we have x cubed plus x to the power 6 over 6 plus c. This is our function. If we take a derivative of it, we'll take derivative of the outside first. So bring down the 6. X cubed plus x to the 5th over 6. The derivative of c, we're not finished yet. We did the derivative outside times the derivative of the inside, which is 3x squared plus 1 plus 0. The 6's cancel, so we have x cubed plus x to the 5th, 3x squared plus 1. Is this what we started off with? Yep, that's what we started off with. So that's our answer. So we found the antiderivative of our function. Example 2. Will this method always work? Yeah, yes, but we have to do some other things first. Find the integral of the square root of 2x plus 1 dx. Here are the steps. Change the radical into exponent. So what is a radical? What does a square root symbol become? Power 1/2, yeah. The square root of x equals x to the power 1/2. Or the nth root of x equals x to the power 1 over n. Whatever the root is. So we have this 2x plus 1 to the power 1/2 dx. Define u. Find du. So what is our u? What is u? 2x plus 1. Our n is 1/2. What is our du? Do we have a 2 coefficient? If du is not present, then add the du and divide the outside by du. Because anything you add to a function has to be canceled by the coefficient outside the function. Our du is 2. So we need to put a du in there. Which is our u to the power n half du. So we have to put a 2 inside there. Since we've added a 2 here, we have to put the opposite of it outside, the reciprocal of it. Because it's not changing the value, it's just changing the way it looks. So now we have u du. Now we have that. So the integral of u du is 2n plus 1 over n plus 1 plus c. So it's 1/2 2x plus 1 to the power 1/2 plus 1, all divided by 1/2 plus 1. One half u 1/2 plus 1 is 3 over 2 over 3 over 2. Since this is a fraction, you bring it out in front as a reciprocal. The 2's cancel. U is 2x plus 1 to the power 3/2 plus our constant. Or if you want to, you could always put it back into the original function of 2x plus 1 cubed all over 3 plus c. That's our antiderivative. So what's the hardest part of this process? Determining what u is. Because sometimes you'll have many parts. Make sure you pick if you pick the wrong u and take the derivative of it, you'll never get the answer. It won't fit anywhere. And if you're very close and you need to add a multiple, you can put it. You could either put a multiplication or division to it, and it'll work. But you have to do the opposite outside. So, Theorem 6 says the substitution rule. If u equals some function g of x, is differentiable. What does differentiable mean? You can find derivative. Why is that important? This goes back to calculus 1. Differentiable means you can find the derivative of it. If you can find the derivative of it, it has to be what? No, that's what the derivative is, the slope. But if you can find the derivative of a function in a open domain, that means it's continuous. Because you can't take a derivative of a function if it has a point or a jump discontinuity, or it modifies erratically or behaves erratically. So if u is equals g of x is differentiable, on the entire domain, and whose range is an integral I. So let's see what this is saying so far. If u equals g of x, if that's differentiable on the entire domain, and whose range is an integral I, and f is a continuous function on that interval, I, I'm sorry, not integral, interval, whose range is an interval I. Yeah, because it has to be the same. So if u is g of x is differentiable on an entire domain and whose range is the interval I, and f is continuous function on that interval, what does that mean? What is that telling us? G is differentiable on and its range. Why is its range important? Well, because remember, this, if we take an integral of something, that's the derivative. That means we're looking for the output of it. So we want the domain of x, f, will be the range of g, because it has to be one function inside of the other. So f is a continuous function on that interval I. Then we have this. Then we have the integral of f of g of x times the derivative of that function, g. It equals the interval of x dx. This is a substitution method. Fu. du. Does it relate to what we just did? How does this relate to the example we just did? Right, exactly. So this is u to some power. This is du, which is equal to u to the power n du, which is exactly what this is telling us it is. Okay, yeah. So the substitution method to evaluate the integral f of g of x times g prime of x dx. Using the substitution method to evaluate that. What's my first step? It's what you said earlier. Find u. What is u going to be in this equation? Because that's what's defined. Then you have to find du. Remember, u is a function of x. So in our equation earlier, we found du over dx, that's du dx, times dx. That's how we defined it earlier. So how does that relate to what we have here? So this becomes, this is g prime of x dx. So what does that give us? Combining steps 1 and 2, we get so g of x is equal to what? It equals to u. G prime d of x equals du. So we have f of u du. Integrate the function with respect to u then the last step is replace the values of u where u equals g of x. So this is what the theorem just tells us. We have to first identify u. If you get the wrong u, you got the wrong answer. So once you find u, you find du, combine the functions, integrate the function with respect to u, and then you get the answer and put it back to the original function. Let's look at an example. Secant squared of 5x plus 1 times 5 dx. Use your cheat sheets, your charts, to tell me what the integral of secant squared is. Mm-hmm. And u plus c. But what is our u? What does u equal? So du would give us what? 5. Do we have du? Yes. Here's du. Here's u. So what we have here is secant squared u times du. Because it satisfies that condition, we can use our chart, which is tangent of u plus c. That was step 4. Step 5 is u is equal to 5x plus 1 plus c. And here's your final answer. Pretty straightforward. It is like I'm not gonna kid you. It can get tricky, but once you step back and look at those 5 steps, you should be able to get it. Yes. This one? Look in the sheets I gave you. This has already been defined. The integral of secant squared is tangent. So there's nothing you have to worry about that. You don't have to do the power rule or anything. There is no secant cubed over 3. We could, we could spend the next class period we can go through and find out why the integral, or actually, why is the derivative of tangent secant squared? Once we see that, then we can work backwards to get the integral of secant squared is equal to tangent. All right, let's look at a little bit more difficult one. Example 4. Find the integral of cosine of 7x plus 3 dx. With practice, I bet you some of y'all see the answer already. Anybody know the answer just looking at it? Yep. Plus C. Yeah, you can't forget the plus C. And you will get dinged on it if you don't put a plus C on the computer. I guarantee you, everybody in this world who's ever taken calculus 2 will forget to put the plus C at the end of it at one point or another. Because you'll be doing a lot of work, and all of a sudden you'll have to get an answer, and you forget the plus C, and you get it wrong. So the solution. First, we have to define what is U. U is inside the function, 7x plus 3. So du is equal 7. Do we have a 7 out in front? No, so we have to add the 7. Because now we have cosine u du. There's u, there's du. Actually, I should write it this way. Cosine 7x plus 3 times 7 dx. This is cosine u. This is du. Yes, because we added 7 here, we have to put a 1/7 out here. Because our first objective, we have to make sure we have the u du part. That has to be defined. If not, then doesn't matter what's in front yet. So our final answer, we have 1/7. The integral of cosine is sine of u plus c, which is 1/7 sine 7x plus 3 plus c. Y'all feel okay so far? Let's go one step further. Example 5. Find the integral of x squared e to the power x squared dx. Oh, I'm sorry. X cubed. So what is our u? Our u is x cubed. So du is 3x squared. We have an x squared. Do we have a 3? No. So we have to put a 3 there. And because we put a 3 there, we have to put a 1/3 out here. Now we have EU du. So it equals there. I just finished talking about that. You're looking at yes, you have to be very careful about that plus C. Yes. From this one to here to here? This right here? Because, okay, yeah, good question. Because what we have here is EU du. That's what we need in order to find EU plus C. So we have 1/3. U is x cubed. Du is 3x squared. And it's all integral of dx. So here's EU du. And all this stuff is du. I just put it out here instead of in front of, I put this here instead of behind it for the EU du. It is 3x squared. It's just that this 3x squared. But now this is the du part. This is EU du. So when I do the final answer, I don't have to put this. I only have to put this. Because we take the derivative of this. The 3 comes, the x cubed comes down. The derivative of x cubed is 3x squared. So the 3's cancel. We're left with x squared. Yeah, that is the tricky part about the e function. E functions are straight up simple, but at the same time, they can be very deceiving. Now, if you thought that one was fun, example 6. What was that? What was that example there? Find the integral of x radical 2x plus 1 dx. Define u. That's the 2x plus 1. So du will be what? 2. Do we have a 2 out in front? No, that's the first part. So we know we will need a 2 out there. Since we have a 2, we had to put a 2 there. We have to cancel it out by put a 1/2 in front. So we have u x u to the power 1/2 du dx. But the problem is this guy right here. We found u. We know du is 2. We found that. So we cancel it out in front. But the problem is, what do we do with this guy? No, we have to put this one, because look at this equation. It's everything's with respect to u. We have to take this equation and solve for x. Put x in terms of u. So we know u equals 2x plus 1. So solve for x. So we get u minus 1 equals 2x. So x is equal to u minus 1 divided by 2. So that's x is u minus 1 divided by 2. 2x plus 1 to the power 1/2. And we have our du. We have 2 dx. We have our du. We can't do anything with this just yet, but we can simplify what's out here. This 2 we can bring out in front, so we get 2 times 2 is 4. So we have u minus 1 times u to the power 1/2 du. This is what we have. We have u minus 1, u to the power 1/2. This is du. So far, so good? Now we can distribute. U to the power 1/2 times u to the power 1 is equal to what? Sorry, I'm still in my integral. When you multiply two bases that are the same, different exponents, what do you do with the exponents? We have u to the power 1 times u to the power 1/2. Add the exponents. So this is 2 over 2, so it equals to u 3 over 2. And then minus u to the power 1/2 du. Follow me so far. Because this x was throwing us for a loop, everything else worked perfect. We have a u du, everything worked perfect. But that x, so we had to put it in terms of u. We took it from what we found here with substitution. And now we have this function here. Go to the next page. So we have 1/4 integral of u 3/2 minus u 1/2 du. Now from here, integrate. So we have 1/4. The integral, well, remember, we have the integral of u to the power 3/2 du minus the integral of u to the power 1/2 du. Using the difference rule. Do you remember what we have to do here? The integral of u to the power n. The integral of u to the power n equals u to the power n plus 1 over n plus 1 plus c. So we have u to the 3/2 plus 1 over 3/2 plus 1 plus c minus u to the power 1/2 plus 1 on the bottom 1/2 plus 1 plus c. Since these are constants, we can just put them out here. So this is 2/2, so it's u to the 5/2 over 5/2. This is 2/2, so it's u 3/2 over 3/2 plus c. What do you do when you have a fraction on the bottom? The reciprocal, so it's 2 u 5/2 over 5 minus 2 u 3/2 over 3 plus c. We can factor out the 2. Which gives us 1/2. U 5/2 over 5. U 3/2 over 3 plus c. Distribute u 5/2 over 10. U 3/2 over 6 plus c. Are we done? Why yet? Why not? We have to put it all back in there like it used to be. So what is u? 2x plus 1. So we have 2x plus 1 to the 5/2 power over 10 minus 2x plus 1 to the 3/2 power over 6 plus 6. And that's our answer. Or that's what we're going to stick with. Okay, that was a long example. But if it wasn't for that x in front, you guys would have had it aced. It says whenever you can do substitution, if you have any more values of x, you have to put them in functions with respect to u, and then take it from there. Let's look at trig functions now. Sometimes trig identities are required. To solve indefinite integrals equations. What do we mean when we say trig identities? Like tangent is the same thing as sine and cosine. We have the cotangent is cosine over sine. Secant is 1 over cosine. Cosecant is 1 over sine. But we have the three big ones. That all stem from this equation. This is the Pythagorean theorem. It's used to define the distances between two endpoints of a triangle, where A is dealing with the horizontal axis, B with the vertical axis, and D is the distance between the endpoints. In a unit circle, the distance becomes the radius. Well, in circles, not unit circles. In a unit circle, centered at the origin, we have radius 1. This is the derivation of how it's all coming together. Now since we're using unit circle in trigonometry, x axis deals with which function? Cosine of x. The y-axis, this is cosine squared of x. Sine squared of x equals 1. There's our first trigonometric identity. So we can use that. We can say cosine squared x is equal to 1 minus sine squared x. Or sine squared x equals to 1 minus cosine squared x. So those are the ancillary ones. What happens if we take the unit circle, the number 1? What if we divide every one of them by cosine? or cosine squared x. So we get cosine squared x divided by cosine squared x plus sine squared x over cosine squared x equals 1 over cosine squared x. Cosine over cosine is 1. Sine squared over cosine squared is tangent squared. And 1 over cosine squared is secant squared. There's number 2 identity. And again, any algebraic manipulation, you say 1 is equal to secant squared x minus tangent squared x, or tangent squared x equals secant squared x minus 1. What if we took the original one and divide by sine squared x? So we have cosine squared x divided by sine squared x. Sine squared x over sine squared x equals 1 over sine squared x. Cosine over sine is cotangent squared. Sine squared over sine squared is 1. 1 over sine squared is cosecant squared. There's our third identity. And then on your chart, the cheat sheet I gave you, you have a whole bunch of other ones. These are just the main ones. All right, so let's look at some trigonometric identity examples. Rule of thumb is this: if you have in a problem like sine squared x, yes, we could say it's 1 minus cosine squared x, but we're still stuck with that. What we want to do is try to find an identity that doesn't have a squared term in it. For example, sine squared x is the same thing as 1 minus cosine 2x over 2. That's one of the identities in your cheat sheets. See, because here it's much easier. Take the derivative of cosine 2x as what? If y equals cosine 2x, find y prime. Cosine u. So this would be the derivative of cosine is what? Negative sine times du. What's the derivative of 2x? So the answer here is negative 2 sine 2x. So it's a lot easier to deal with derivatives when we don't have exponents. Example 7. Find A, the integral of sine squared x dx. What's the first thing you're going to do? Okay. Because we could have done 1 minus cosine squared, but that'd be a little bit more tricky. It wouldn't give you a wrong answer. It just take a little longer to get there. Okay, we have a denominator, so we could bring that denominator out in front. What'd you do next? This is the difference rule. So I could split them up. What is the integral of 1? What function has a derivative of 1? What's the integral of 1? Or what function do I give? If I give you this function and you take the derivative, it equals 1. X. Right. Minus the integral of cosine 2x. Well, this we can use substitution. We have cosine u. We need du. So if u equals 2x, what is du? 2. So we have to put a 2 out in front and a 1/2 outside the radical. Because now we have cosine u du. The integral of cosine u is sine u. And u is 2x. I'm going to distribute that through there. So we have x over 2 minus sine 2x over 4 plus c. And there's your answer.
Earlier, you said that u dx is what du is, right?
Yes, yes. Because remember, you have cosine u du. Because du is du, it's a function of x dx. So the derivative of u with respect to x is 2. So it's cosine u 2u dx. So that 2x, 2 dx is our du. No. Earlier, well, we went through the whole thing. We went through the whole thing here that du with respect to dx times dx. Just on a very high level or low level algebra, the dx's cancel. So that's the same thing as just saying du. So it would be grammatically correct to put du over dx times dx, but that's the same thing as putting du. That's implied that it's du over x. But it's all, because remember, the function of u is a function of x. So du is a derivative of x, and the whole function is a derivative of x. So that's why you don't have to put dx, all this dx stuff. You do. You do. That's why when we have, as long as we have an original function, when we put it into when we put it in terms of u, you notice there's no dx here anymore because the du part is du dx times dx. So here's the derivative of u, and the whole thing is with respect to x. So this whole part is takes care of that. Because we don't want, when we convert it to u's, we don't want x's anywhere. Because u is already implied that it's a function of x. That's a great question. Where's the dx? That takes care of them because when we do the conversions, this is du dx, not dx du. So the cosine u, the u was 2x. The derivative of u would be 2. And that basically that's the du dx part. Du dx is equal to 2. So I don't have to put that there. That's just what it equals. So cosine u du dx is this part here is 2. And this is cosine u. And the whole function is still a function of dx, but it's taken care of because we changed it to u.
And so when you write down du equals 2, it shouldn't be du dx equals 2. It can just be du.
Right. Yes. Yes. Because again, we take a derivative because u is a function of x. All right, let's look at another one. B. Integral of cosine squared x dx. Yes, you could use your cheat sheet and see 1 minus sine squared, but we don't want exponents. So what is cosine squared x being rewritten as? What is u? Or what is this equal to? Right. Right. And we do the same thing from here on out. So what's going to be different in the answer here? That sign changes from negative to positive. Integral of 1 is x. And as we've seen here, the integral of cosine 2x is sine 2x over 2 plus c. and distribute the coefficient. Here's a question. When I distribute the 1/2, why don't I distribute it to the C? Yeah, because it's any constant. So C over 2 is still a constant. So that's why we don't worry about doing that. So that is how we use the trig rules to manipulate our equations. Let's do a couple more and we'll call it a day because it's almost noon already. You may have to do some algebraic manipulations to solve your equation. For example, the integral of dx over e to the power x plus e to the negative x. We can't split them up. You can't split them up because the denominator is a sum of two exponential terms. So they have to stay together. So what do you think we can do? That is, I didn't think about, I just thought about the same thing, but I didn't think about it earlier. Let's try that. We have dx equals on the bottom, ex plus 1 over e to the power x. In order to do that, we have to get common denominators, right? In order to add to the bottom ones. The denominator is e to the power x. So what do we have to do to this one? So we got d of x. This is e to the 2x over ex plus 1 over ex. Since we have a common denominator, we have e to the 2x plus 1 over e to the x. Leave the top alone, flip the bottom. And that's what we want to get to, right? Because what we did here, the only mechanic thing we had to do here is multiply by ex over ex, multiply by 1. We could have done the same thing here. E to the x over e to the x times dx ex minus e negative x. e to the x dx, e to the power 2x, negative x plus x is e to the 0. So it's ex dx e2x minus 1, which is the same thing. But no, it's what you said was not incorrect. As long as you follow the rules of math, you'll get the same answer. So no matter which way you use, we're still stuck with this equation. Oh, I'm sorry, it should be plus on the bottom, not minus, plus. Plus in the original. Can we use EU du? So u is going to be e to the power 2x. Du is supposed to be 2x e to the power 2x. Oh no, e 2 times e to the power 2x, right? E to the power x. So let's see what we have here. We have the integral of so we're going to say that, okay, we're going to say u is e to the power x. So we have 2, u equals 2 plus 1. Therefore, if we did this, then we just have du on top, e to the power of x. That'll work. If we did that. 2 e2x 1/2. Yeah, if we left it as 2x, then we get more trouble. Since we have e to the x here, e to the 2x here, we simply say that u is e to the power x, and if we square it, we get u squared. Because e to the power x squared is e to the power 2x. Remember the rules. Power to a power is simply the product of those two powers. So do we have do we have any more charts that anything looks like this? Du over u squared plus 1. I don't have my chart here. No, I mean, we have what we're supposed to, because now if we took this one, then du would just be 2u. But there is a identity, trig or algebraic identity. Look in your notes for that in your chart. Tangent inverse of u plus c, right? Once you find du over u squared plus 1, there's also du over u squared minus 1. There's a whole bunch of those. And that's why always, when we first can find a conversion, look in the chart, because that may save you a whole bunch of time. So the answer is tangent of e to the power x, inverse tangent of e to the power x plus c. There's your answer. We get out at 12, don't we? 2:50? Oh, it's almost noon. But yeah, that's as far as we can go here. Because the next couple of examples we only have a couple more, but these get longer now. The next one is the integral of secant x. Actually, do you have the integral of secant x on your table? So it's ln of secant x plus c. No. Plus tangent. Yeah. It has to be secant x plus tangent x plus c. All right. Because the long drawn out derivation of this is secant x dx. You have to multiply by something with this equation so that we can use a transformation. So this is secant x times 1 . This 1 is actually a huge equation of secant x plus tangent x, secant x plus tangent x. Again, those are identities. Distribute through there, we get the integral of secant squared x plus secant plus tangent. It's just this step right here. Because secant and tangent are on the same identity line. So since that's squared, so it'd have to be du over u. So u would have to be secant x plus tangent x. That's what we just did there. Yeah, and the derivative would give us derivative of secant squared and tangent, secant tangent. Du over u, the absolute value of u, ln u is du over u. That's the identity from the chart. So it's going to be ln absolute value of u plus c. And u is ln secant x plus tangent x plus c. So that's the integral of secant x dx. If you look at your chart, you'll see like the integral of cosecant x dx. That's going to be the negative natural log of cosecant x plus cotangent x, because it just goes to the opposite ones. That's how cosecant and secant are related.
Instead of being negative, saying natural log of absolute value of cosecant x minus cotangent x.
You can't do that.
Same thing.
Mm-mm.
That's what's up here.
With a minus in front? Because that would make it, this would mean, let's see. Because I always learned just as just the opposites of those, just positive negatives. So this would make it negative, which would make it cosecant over cotangent, which is oh yeah, it would work. Yeah. So yeah, you put it inside there or there. I just learned it's easier because if you just leave it as plus, the opposite of secant is cosecant, cotangent, and they're opposites. So that's why I learned it. Yeah, actually, that's I never thought about that. Yeah, yeah, they'll give you the same answer algebraically. See that again, the calculus part just gets you going. It's the algebra part, the manipulation of the functions that is the important part. And then the natural logs of sine and cosine are the secant yeah, secant cosecant or tangent cotangent. I mean, yeah. So that's all the time we have. It's noon right now. I don't know if you guys have another class. We're almost we're pretty much done with this section. We'll do some more examples next time, and then we'll do the next section. We'll finish up chapter 5. All right, everybody, have a great, safe weekend.